Okay, welcome to the 10th class of Big Data Analytics. So we are about 2/3 of the way. We are actually going to share screen one. Okay. Okay, can you see that? We are around here. There it is. Okay. So we are going to cover just one more essential bit of machine learning technique. Has to do with unsupervised learning. There's another one on machine learning, I think 2 classes down, covers a bit like LSTM, GNN. So these are more like the architecture that deals with let's say more specialized. You can say more specialized in the sense that CNN is, for example, used for visual recognition. So looking at picture or video frames. LSTMs deal with number, but more like a time series, like financial time series. Price of stocks or price of Bitcoin or whatever. GNN deals with the more general concept of relationship and so forth. So you can imagine that this is where you get to big data stuff, and also NLP, natural language processing. But looking at most of the project that you've been proposing, the data set you are working with are pretty much sort of numerical, okay, maybe a classification type thing. So I think with this, we'll cover, I think, most of your project work. Okay, most of your project work. So today we should pick randomly about 10 of you to talk about what you intend to do with your project. Okay, so let's go back. Let's go to this little side note. Okay, right now first I have to make a little bit of a correction to last week's lecture. I kind of got a little bit carried away. When I did this thing where you have data set and so forth, right? And we have another one data set. And I want to say that you make a decision tree. Well, when I was drawing a decision tree, I was being a bit loose. I was drawing it sort of like at an angle. Well, decision tree doesn't do angle. Okay, normally it doesn't do the angle. So you would have to do something like this, and then this, and then. Because after all, when it's creating a partition, it's not creating a partition of AX1 plus BX2. It's actually creating a partition on X1 or X2. Okay, so it doesn't really do the diagonals. So this is the note I have. I kind of got carried away when I was drawing the picture. Okay, so decision tree doesn't really do diagonal cuts. It does vertical and horizontal cuts. Okay. Why? Because if you're talking about diagonal cuts, you have to say something like AX1 plus BX2 is greater than 5, something like that. It doesn't. It only picks one at a time. For example, X1 is greater than 5, and then it asks, Y1, X2 is less than 10 or something like that. So it's checking condition on one variable at a time. So that's like separating left from right, up from down. Okay, so this would be like if this is X1, so it's less than equal to for X1, this is less than equal to for what X2. Okay, so it doesn't do that. That's a little more. Now that brings me a little bit back to the idea of a decision tree that I tend to not cover very much, but I think maybe looking back, perhaps it's also one of the most popular tools. So I should spend a little bit more time today. So even though today we're going to be talking about principal component analysis and dimensionality reduction, let me just do a little bit more on the decision tree here. Okay, let me go back to elaborate just a tad more. Okay, and again, random forest is just an extension of having more than one trees, right? And they have gradient boost tree, that's a bit more complicated. But the decision tree itself is quite popular, and for good reason, okay, for good reason. Even though it's not that convenient in terms of, it's not that efficient sometimes in terms of creating a partition. For example, let's go to that picture again, because it can only do the horizontal and vertical cut, right? It cannot do this. So if you want to create this kind of partition, you have to do many of them at the same in sequence. You have to go like this, and then like this, and then like this, and then like this, and then like this. Eventually, you approximate the diagonal line, but it takes you a while to get to that partition. Okay, so you can't, because that decision tree can't do diagonal cuts. It can only do vertical and horizontal cuts. You can kind of like approximate, you know, diagonal cuts with a sequence of this. Okay, so it's not all that efficient. Okay, but it will get there. It will get there. Okay, so I'm not going to put more emphasis on decision tree because it's efficient. I'm going to put more emphasis on decision tree for a different reason. And that reason has to do with the fact that sometimes, okay, when you have y is equal to some model, model of x, right? Now, your job is to build this thing. Your job is to build this thing as a data scientist, is to create the model. But sometimes when you use it in real life, people get a little bit nervous. You know, where do you get this? If you get something like y is equal to, you know, if you get something like, well, we haven't started the Mathematica, so let's start a Mathematica show. Okay. New notebook, right? So if you have some function, right, y is equal to f of x, and people don't know what that function is, they can get a little bit nervous. But if you tell them that y is actually you know, a x1 plus b x2, right? Now this is not as powerful as that one. Okay, this can be any general function. This can only be like a function that takes a coefficient for x1, that's a, coefficient for x2, but from a user perspective, they get an intuition and they get more comfortable. Okay, they know that, oh, okay, I see what you mean. You mean that if you have more x1, then let's say a is positive. Okay, let's say a is positive. If you have more x1, then y will increase. And say let b is negative, then you can say something like, well, if you have more of x2, then you have less of y. So there's a lot more intuition. And this goes under the concept of, you know, something like, this is quote unquote black box. Okay? And this is something like, they call it white box. Black box means you can't see what's working under the hood. White box means you see exactly how the model works. This is rather silly, in my opinion. Okay, this is rather silly because, first of all, black box isn't really black box, right? It's just black box for people who do not understand it. Okay, and second of all, what is your purpose in life? Your purpose in life is to just know how the algorithm work, or you want to get a good prediction, right? So if you can't really tell what the model is doing because you don't have the mathematics or whatever, you don't understand the mathematics, but at the end of the day, you want to get a better prediction, right? So if this is more powerful, it's more accurate, less intuitive, okay? And this one is more intuitive, less accurate. Okay? Which one should you choose, right? Well, I would say in real life, you should choose the one that's more accurate, okay? And if it's not intuitive, work on your intuition. try to understand it, try to understand why the model works. And this is one of the reasons why, you know, basic machine learning and data science is critical, even if you are going into you know, sustainability track or health science track or smart city track, because there you still want more accurate model. Okay, if you don't have the right intuition, you find the model is not intuitive, you work on it, right? You work on it. So this idea that you should prefer white box to black box is, to me, is total nonsense. It's total nonsense. Having said that, okay, so let me put this, let me put that in my notes. Okay, it's nonsense, it's nonsensical to prioritize, okay, intuition over, say, accuracy or performance. In most cases, okay, something like MLP, multi-layer perceptron, would be more accurate, okay, but less intuitive than decision tree. In most cases, okay, in most cases. So it makes no sense to choose decision tree over MLP. It makes no sense, absolutely no sense, right? But whenever you get comparable accuracy performance, and DT's intuitiveness, I guess, intuitiveness is a luxury you can afford. In other words, the way we work, and this is what I've done in my professional, you know, consultancy and data science career, is I try whole battery of technique, okay, a whole battery of techniques, and then decide on merit. Okay. If and only if, okay, say something like MLP and DT deliver similar accuracy, then I would present DT as the model for, say, client or application. In other words, we don't sacrifice model performance. Okay, we never do that. But if we get similar, okay, so you know, you get something like a testing accuracy of, you know, 92% versus 93 or versus 91, that's really nothing. That's really nothing in life. Okay, that's really nothing. I would prefer to use decision tree, because then decision tree is intuitive, it's easy to explain. Then you can sort of like give it as a recipe for your client to go and create some kind of insights. Okay, so when that happens, yes, decision tree is very good. So let me then elaborate a little bit more on why decision tree is a good thing. Okay, so this week I decided to go back a little bit and say, and that's why I asked you to go to this paper with code, right? Paper with code. Now, this is something that I did for let's click on the link. Have you guys downloaded? Yeah. I haven't, so sorry, I just sent you the link, but I haven't downloaded. So let me go to Line. oops. Okay. Big data analytics. So let me go to this one. Okay. So this paper here, okay, this paper here, well, basically it's something that we did for asset management application, but obviously it's a private data set. So I use this technique on breast cancer data. Okay, I use it on breast cancer data, and because it's got pretty good accuracy, I use a decision tree. Now the whole paper is about creating what's called fuzzy conviction score. This is sort of like enhancement on decision tree. Okay, but so you can read the paper if you like, but the thrust of the paper is to enhance the performance of decision tree. But I want you to have this paper, because this paper contains this graph, this picture. Okay, this paper contains this picture, and this is basically a garden variety decision tree. Okay, the way this data set works is that it measures certain attributes about the cells, you know, whether or not the cells, this is from the diagnosis of breast cancer. So you take a tissue sample, right? You see the size, you see the nucleus size, if it's big or small, or if it has different variation in size and so forth. And you measure all that. So again, this is like your project, a lot of your project, this is tabular data. And the decision tree then looks at all this, and then decision tree looks at all this and then makes a partition. Okay, so instead of partition x1, x2, it first makes a partition between this thing called, called uniformity, and you can see this uniformity of cell size. Okay, so this would mean that this is like x1. Okay, x1 is a measure of uniformity of cell size. So if cells are uniform, that means you take the breast tissue, right, and you sort of like make you go look at the microscope and you estimate the size of individual cells and see if there's a lot of variation. Some big cells, some small cells, or pretty much the same size. So x1 would be uniformity of cell size. If it's less than 3.5, it goes to here. This is the true. Okay, so this would be something like on the x-axis, right? You put 3.5 over here and you make the vertical line. Anything that goes to the left of that goes into this block. Anything that goes to the right goes to that block. Now, you would notice that it has, in each block, it has quite a few information. Let me make it larger. Okay, so 0 is the name of the decision tree junction. Okay, so 0, 1, 2, 3, 4, 5, 6. This is like a reference. This is like reference. Again, why is this a decision tree? Because it branches, right? Now this is more like a root because it branches down. But if you flip this picture upside down, it branches up. So that's why it's a tree. Okay. So 0, 1, 2, 3, 4, 5, 6. That's just a reference of the box, so you know which box I'm talking about. So look at box number 0. This is like a starting junction. The starting junction looks at what's called uniformity of cell size and asks, this is the question, less than equal to 3.5. This is actually a question. And right now it has 478 women. Okay, so this is sample of breast tissues, you know, cells, little bits of cells from 478 persons. Okay, Now, this one happens to be the data that is called label, meaning that you know, again, we're talking about supervised learning, right? You know that from 478 women, 311 11 of them do not have breast cancer. Do not. Okay? Do not. I think positive means yes. Yeah. And 167 of them is are diagnosed with cancer. Okay, so this is not unknown. This is labeled. So 478 women, 311 of them did not have breast cancer. 167% of them, 167 of them have breast cancer. Then we take the sample from their tissues, okay, and ask, okay, is the uniformity of cell size less than 3.5? If it's true, the class is non-target, meaning it goes to no. Okay, it goes to no. If it shows to no, it goes to non-target. Okay, non-target would have color orange, okay, or red. Target would have colors of blue. Now, in the beginning, you have 167 target. Okay, you have 167 target and 311 non-target. So it's mostly non-target. So it's a little bit more orangey, but it's not pure orange, right? It's sort of like a blurry color. So this is like a mix of orange and blue. Okay, now go to the decision tree, say, true, the uniformity of cell size is less. So it's not uniformity cell size is less than 3.5, it goes to here. Then they measure bare nuclei, I don't know what that is, it's the size of the bare nucleus, I guess, is less than or not. Okay, so now, right now, they're actually 327. So out of 478, 327 goes down this way, and 151 goes that way. Okay, but still, okay, you have more here, you have less there. And the idea is that if you look at it, the composition has changed, right? This is like 2 to 1, I think, right? Ratio, 2 non-target, 1 target. This is like what? This is like 12 times as many non-target. So it's a lot, it's sort of like coming to non-target, okay? It's a lot more orangey. On the other hand, when you go to over here, okay, you have 142 cancer and 9 non-cancer, okay? So definitely this is a lot more target mix, more target in the mix. So it's 142 to 9. The odds of being cancer is very high over here, okay? So it's very blue, okay? And then it asks this question, bare nuclei, go to the left, go to the right, marginal adhesion, go to the left, go to the right. So you can see why in this case, now, there's a number here that I haven't explained, okay? Gini is a number between 0 and 1, okay? It's just a magic number between 0 and 1. If the class is all mixed, meaning cancer and non-cancer evenly mixed, it's the maximum value of completely mixed up is 1. If there's only one class, either all cancer or no cancer, but only one type, the number is 0. So basically, as you're going down this partitioning, you want to decrease Gini. That's the name of the game. You start with Gini of 0.45, you break it down this way, you get Gini that's even lower. Why is it lower? Because it has less mixing. Okay? When you have 2 to 1 mixing, it's not very pure. So they call this Gini impurity. Gini for Gini impurity. So for 2 to 1, right? So 2 non-target, 1 target. So it's 2 to 1. So it's quite mixing. It's kind of messy. Everybody mixed together. So it's got high impurity. Now it's got 300 non-target and only 25 target. So it's more dominated by one class. So the Gini is better. It's now to 0.14. Look to the blue side, it's the same thing, except it's the opposite now. You have more cancer. Again, it's more dominated. It's 142 to 9. Now, if it were 151 to 0, the Gini would be perfect. It would be 0. Okay, but it's not perfect yet. Yeah, it's not perfect yet. It's 142 to 9. That corresponds to a Gini of 0.112. Okay, I'll show you how that's calculated. Okay, right. So, well, we can actually do that right now. Let's do that. Let's do that right now. Let's look at this number 9 and 142, right? So, if you have number of OK is equal to 9, yeah, and number of Cancer is equal to 142. Okay. Now, proportion of OK is equal to 9, right? Plus correct, right? Okay. Likewise, probability or portion, let's call it just portion. Okay? It's a probability because if you pick the person randomly from this room, you have high probability of picking a cancer patient, right? So this number, cancer, okay? So we have this. Well, a Gini impurity is equal to POK times 1 minus POK plus P cancer times 1 minus P cancer. Okay, and that number, let's make it numerical. 0.112. 0.112. Okay. Now, if you want to get the original one, right? 4.5, we'll say something like 311.166, 311 and 167, right? And 455. Okay. In fact, Gini is what's driving this algorithm. The reason that the algorithm choose uniformity of cell size less than equal to 3.5 is because by choosing to look at uniformity of cell size and making the separation between less than and greater than 3.5, it's making the best reduction in Gini. And that reduction goes from 0.455 to a weighted average of these two numbers. Okay, so it's basically the original Gini. So this is the original Gini, right? And the improved Gini impurity is equal to, well, you separate this way, so it's 151 divided by 478 times new Gini. What's new Gini? 0.112 plus, how many come this way? 327, right? So 327, and what's the Gini this way? 141. Okay, so the Gini, according to this algorithm, this criteria here, uniformity of cell size, is a single cut that's the most powerful in the sense that right now, if you want to improve the Gini impurity, make it smaller, okay? You can go from 0.5455 down to 0.131. Again, 0.131 is a weighted average of these two numbers. Okay, use that. That's the most powerful. And then you keep going. So this is why, again, given that you have similar performance, would you rather have something like this or say a multi-layer perceptron? You wouldn't like to have multi-layer perceptron because you can't really, dig deep. So this is sort of like very friendly. This is almost as friendly as regression equation. Okay, regression equation y is equal to a x1 plus b x2 plus c x4, whatever. That's very transparent. This is also very transparent. Okay, so again, my principle, it should be the principle of every data scientist, is never sacrifice performance of the model for the ability to explain it away. But if and only if, okay, MLP and DT deliver similar, okay, then I will present DT as the model. So that's why I want to show you this. Now, Gini impurity is one example. There's another way of measuring how well you separate, right? So again, this is like a mixed population, right? This is more sort of like one class. Okay, this is more people who are not cancer. People who don't have cancer stick together, and people who have cancer stick together. So it's sort of like discrimination, right? So the more discriminating the separation, the better. Okay, this is not society. So the more unsegregated, the better. Okay, so does Gini always improve? Well, it tends to improve when you go down, and you keep going. Ultimately, you can make all the partition to get the pure class. But that would be too much, right? That's sort of like fitting a single data point. So you would usually stop at maybe 2 or 3, 40, okay? Or maybe 5, something like that. Okay, so that's it. That's how you read a decision tree. Now, if you really like decision tree, okay, and you're working with Mathematica, okay, I would suggest you look at this picture, this website, okay? So, oops. Yeah. So this is an example, work through example. So this is like a decision tree, except instead of one branching, you got one branch, 3, 4, 5, 6, 7, and so forth. This is a real problem with GDP data, so it's a real data kind of thing. Okay. Now, let me make a note that people who use Mathematica usually use more advanced model than decision tree. So they don't pay that a lot of attention to decision tree. So if you really want to play with decision tree, you might want to consider Python scikit-learn, because the visualization is prettier. Okay. So visualization of a trained decision tree is prettier, it's more prepackaged. In fact, this picture that we use, your TA and I use for the paper, is drawn using Python's scikit-learn library. Okay, scikit-learn library, because it's it's actually prettier and more ubiquitous. Okay, so if you look at this paper, what the paper does, it adds additional capability by looking at how far the data point is from the separation, and creating some kind of conviction score to enhance the separation within the group. Okay, so right now it's separate between 142 versus 9, right? So, but it's still good. It's still mixing here. What the fuzzy conviction score does is actually further distinguish points within the same block. Okay, but it starts from the baseline decision tree, and that's why you should have that paper on hand. Okay, so this would be something like based on this. Okay, now if somebody else comes in, now this is a scene data, right? So the testing data would be another person, another female patient comes in, doesn't know if she has or does not have breast cancer, takes the biopsy, takes a bit of tissue from the breast tissue, right? Measure uniformity of cell size. If it's greater than 0.5, then it comes over here. Oh, doesn't look very good. Doesn't look very good. Okay, but if it's less than 0.5, then it looks good. But again, if bare nuclei is greater than 2.5, that looks bad again. Okay, so in this case, orange is better because orange means no cancer. Okay, so that's that. So so I want to go back a little bit, and I think I owe you from last time also is to look at ROC or AUC. Now that one can be summarized by just looking at the picture. Okay, this is, I think I just got this from. You see that in the paper, in the paper here, right? In the paper here, I also use this picture, this ROC picture. Okay, but I just want to show you. So if I look at this, if you look at this, you should say that this is a very good model. Okay, the model that we did, just looking at the picture alone is good, but I'll show you why it's good. So let's look at what the decision. This one is called ROC curve. ROC stands for ROC. Why am I? Oh, this is in Bing. I don't like Bing. So ROC curve. Receiver operating characteristic is kind of engineering term. Okay, it's kind of engineering term. Right. So what it does, it plots true positive rate and false positive rate. Okay. Now let's look over here. True positive rate means you get true positive from 0, no one at all, and 100%. Okay. So it's true positive. Of all the positive, you get true positive. False positive means what? If you get 100% false positive, that means all the non-cancer people, you would say are cancer, right? Okay, true positive means cancer. Yes, you say it's cancer. You predict cancer. False positive means non-cancer. You predict cancer. Okay. Now, you can get worse. You get 0 true positive rate. You get 0 false positive rate. How? By saying nobody has cancer. Right? Because if you say nobody has cancer, the person who has cancer, you would say doesn't have cancer. So it doesn't have true positive. But on the other hand, you also don't have false positive. So this is the person who say no cancer. Doesn't even look at the lab result. Okay. Now this is another doctor. This doctor say everybody has cancer. Doesn't look at the lab result. So this person is going to get all the real cancer, but also everybody who doesn't have cancer will be told they have cancer. Now, again, last time we talked about the balance between what's worse, right? In the medical sense, false positive is better because you can take more tests, okay? But in the judicial system, you don't want false positive because that means you're sending good people to jail, okay? Positive case means, yes, this guy's a criminal. Anyway, so if a model is over here, okay, I'm just pointing at one, okay? The model here, if you think about it, a model sort of like ranks a person from most likely to have cancer and not likely to have cancer, okay? And you can say, you can screen, take the top half or take the top 10%. So you can be more stringent, right? So let's say you are over here. This is your model. This model would actually have 0.6 or 60% true positive. Okay, so of all the positive, you get 60% of them. Okay, that's pretty good. Okay, and false positive is 20%. Okay, so people who don't have cancer, 1/5 of them gets a false alarm. Okay, now if I go from here to here, this is the same model. Okay, I make it more stringent. So the value has to be really high. Okay, sorry, less stringent. Okay, less stringent. So I say cancer a lot more. So what happened? I get more false true positive. That's a good news. But I also get more false positive. That's bad news. Okay, so along the green line is the performance of one machine learning algorithm. But how you use it depends on how stringent you are. If you're more stringent, you're not likely to say positive. If you're less stringent, you're more likely to say positive. Okay, but it's always a trade-off. It's always a trade-off. So if you want more true positive, you get more false positive. If you want to reduce false positive, you also get less true positive. You can't get more without worsening the other. If you have a better model, you don't move along the same line, you actually go to a different line. So this is a better model. This model, in other words, accumulates true positive really quickly before it starts to accumulate false positive. You think of it this way, right? So nobody has cancer and you start calling, yes, somebody has cancer. Now, a good model would keep calling those who have real cancer. Yes, cancer, yes, cancer, yes, cancer, yes, 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 before start calling people who don't have cancer. Okay, so this is a good model. This is the best model out of all these three. Okay, now there is this orange line, which is worse, right? Because you're getting as many true positive as you're getting false positive. You're just getting, random. A truly random would be this 45-degree line. Okay, so you get true positive as likely as you get false positive. This is completely random. Okay, now you don't have a line that's below here. In real life, you can actually get a model that's worse. That means it's a model that's worse than random. Okay, you throw that thing right away. Okay, you throw that thing that way. You don't throw it. You don't show it to your mom. You don't show it to anybody. Okay. Now, so this is a random classifier. So every time it gets more true positive, it gets more false positive. Okay, so this is a decent model. Well, decent in the sense that it's better than random. This one is more reasonable. This is more useful. You see something like this, it's useful. Okay, you start making decisions. You start, in other words, you get more true positive for every false positive. So you're starting to say, this is a good model. This is really good. Okay. The more you go this way, the better. Okay, so the perfect model will just keep going this way. Now, this is what's called the ROC curve. Okay, so obviously, if you take the area under the ROC curve, okay, so you take the AUC, ROC is equal to receiver operating characteristic curve. AUC is equal to area under the curve. What curve? Okay, so the perfect area under the curve is 1. A random would get you 50.5, right? So half the area. This is 1 times 1. So if you get AUC 0.5 means you are at random. Okay, AUC is equal to 1.0 means you have okay. Now, if AUC is greater than 0.7 means you get paid. Below that, you can still get paid, but and AUC greater than 0.9. Now this is kind of rough number, right? Means yeah, something like that, right? So that's what this comes down to. So this by the way, this is for any kind of classification, okay? But it works for binary classification. If you have multiple class, then you have many lines, and you have to sort of like inspect them all together. So it's a little bit more complicated. Okay, so that's it. That's it. Okay. So now let's go to the real lecture part. Okay, anybody have a question? So if you have in your project, if your project is some kind of classification, now let me write a note for multi-class classification. You have many ROC, AUC feature. Okay, but you can also consolidate. Okay, but that's a little bit of a fuzzy area. Okay. Kind of okay. But if you don't have that many classes, you have 2-3 classes, it's good to examine them separately. Okay, so this would be like, instead of cancer versus not cancer, you would say cancer type A, cancer type B, cancer type C, something like that. Okay, so that's it. So now let's go to PCA, principal component analysis. Now, let me just play with this by where's my date? Where's my okay? It's my bits and pieces, right? Save as bits and pieces. So that now let me show you something. Okay, I'm just going to first of all set directory. I tend to do okay, and import. Now I have this file here, yield curves. Okay, let's say my data. Import yield curve. Yes, you. So let's look at dimension. I tend to do this, by the way. If you see in my project worksheet, I tend to do this so that I make the assignment and I also get out the dimension. Okay, so it has 45,000 rows and 8 columns. Okay, let's see what they look like. Okay, let's say data. Let's say let's look at the top 5. Okay, right. So this is the data from a real life in real financial data. Okay, this would be yield. Yield is like interest. Yield is like interest. Okay, what this means is that if you invest in 3 months, you get 1.17% yield. So that means that if you invest 100 baht today, right? In 3 months' time, you get something like 1 plus 0.0107. Okay. Now, but this is the interest. This is the interest. This is the principal. This is the interest. This is the 1.07% for 3 months. But 3 months is only what? It's only 1/4 of the year. So actually, it's 1/4. Okay. This is how much money you would get. Okay. If you invest in 100 baht, in 3 months' time, you get this. On the other hand, if you invest in here, okay, this is 2-year yield, you would get this 202, and because you're investing for longer, you get 104 baht, right? So this is a year interest rate per year, so you have to adjust for amount of holding. Okay, so this is actually what's available for the day. Now, the day after, this market has moved. So let's look at list plot. Let's look at list plot. List plot data to, right? Because we don't need the first one. Well, actually, list line plot, sorry. List plot doesn't look nice, but let's make it. Okay, let's look at this line. Okay. Ooh. This line plot. Okay, so let's say right. This line plot 3D. That's better. Yeah. Now.
Where did you get the yield curves.csv?
Oh, okay. I'll give it to you. This is download from internet. I'll give it to you. Sorry. Okay, you can play with this. Okay. Now, if you look at this line here, okay, all right. Let's make it a bit less. Let's just say 6. Okay, so 2, 3, 4, 5, 6. 5 days. 5 days. This is day 1, day 2, day 3, day 4, day 5. Now let's look. Now this is actually, I'm just listing 1, 2, 3, 4, 5, 6, 7, 8 of them, right? So if you look closely, okay, this is 1, 1.3, 1.6, 2, 3, 5. Okay, so this is the interest rate. Okay, range 0 to 5. Okay, so on day 1, if you invest in 3 months, you get this many percent. So 1.37 is 1.07, and then 1.35, and 1.6, and then jump to 2, and then to 3.17, and then 3.57. Okay, so this is what's called a yield curve. Okay, this is what's called yield curve. Just look at one of them. Okay, just look at one of them. So this is the yield curve on day 1. Now this is the yield curve on day 2. This is the yield curve on day 3. Okay, right? You see that? Okay. Now, if I want to plot this, okay, but instead of looking at the yield and then move in time, I want to transpose it. And if I transpose it, okay. If I transpose it, hold on. Let's not make it 2. Let's make it 100. This is better. Okay. If I transpose it, remember it goes like this, right? If I transpose it, it's actually going to plot this line, this line, this line, this line, this line, this line. Okay, so if I list plot it, it first plot this, of course, horizontally. If I want to plot what happened, the movement in time, this way, this way, this way, this way, this way, I take the transpose. So basically, this is 3-month yield. Okay, it starts from 1.07. Okay, so that is start here, starts here. 107, 121, 121, 122. 107, 121, 121, 122. It just keep going. So this is every single day. This is every single day. This is every single day. So this is 3-month yield, 6 month, 1 year interest rate, 2, and 4, 5, whatever. Okay. So let's look at long-term evolution. Let's say 3,000 days. Okay. See that? See that? Okay. So what it means is that if you look at it, this is the beginning of the data period. This is way back. This is present. This is going back. Okay. If you go back many years, so say 3,000. Let's say this is today. Okay. 3,000 days. That's what you got. 250 trading days a year. So that's 3 years. Sorry, 12 years. 12 years, right? Because you get 250 trading days a year. Okay, so 4 years is 1,000. So this is about 12 years worth of data movement. So you can see that in the beginning, the short-term interest rate is much lower than the long-term interest rate. Okay, and then what happened? The short-term interest rate goes up, almost catch up with the long-term interest rate that actually comes down. Then they all go up together. Okay, so this is sort of like a movement, right? So this is called short-term interest rate. This is sort of medium-term interest rate, and you go to the end, that's like a longer-term interest rate, like a 10-year. Okay. Now it's not evenly spread, so it's 3 months, 6 months, 1, 2, 4, 5, 7, 10. So think of this as a long-term interest rate. This is like if you're committing to fixed income or bonds, right? For 10 years, you get this. But if you only commit for 3 months, you get that. Afterward, you get your money back and you can decide whatever you want to do. Okay. So for long-term commitment, you generally get higher interest rate. That's just fact of life. Okay. Because you're making the long-term commitment. Okay. So let's say this is day 1, day 2, day 3. You would see that for the first, I don't know, 200 days, the short rate will be going up and the long rate will be coming down, roughly speaking, okay? Until they get very close, get to about 1% difference, and they both go up. And now, look, this year here, the interest rate is almost flat. It's called flat, meaning the line here is almost flat because the long-term interest rate is the same thing as short-term interest rate. Anyway, so, you know, you can see that this has a very intricate movement, right? It has, you know, 12 years worth of movement, 15 years worth of movement of 1, 2, 3, 4, 5, 6, 7, 8 variable. Okay, so right now, they mention okay, so you have 8 variable, you have 4,500 days worth. Okay, so actually this is not even 12 years, this is 16, 18 years. Okay, yeah, 18 years. Okay, worth of data. Okay, so that's okay. So that's where we are today. This is 18 years ago, days ago, 18 years ago. Okay. Now, you can see that it has a lot of movement, right? And how many degrees of freedom does it have? You actually have 8 random variables in time, i.e. 8 stochastic. Okay. Now, you don't know this word yet, never mind, okay? But it's a random variable in time, meaning it's random, and you have different value for each time. So you have 8 stochastic process. Okay, you have 8 of them. Okay, so you can think of it as working in 8 dimensions. Working in 8 dimensions. Okay, because things are moving. But okay, so let's take 3 months, 6 months, 1 year. Was it 2 years? 4 years? Year, 7 years, 10 years. Yield T 1, 2. Okay. In principle, you have 8 dimensions, right? Across time. Yeah, 8 dimensions. Okay. But if you think about it, they are not 8 different animals. They're kind of related. In a way, you know, you can think that if this is a short-term interest rate, this is a long-term interest rate, you kind of expect that the medium-term interest rate will fall somewhere in between. It may not, okay? So this 4-year interest rate may be higher than the short end and the long end, but most of the time they kind of like have this kind of relationship, you know, it's kind of monotonic. So if you think about it, maybe they're not moving independently, right? They're not moving independently. And if they're not moving independently, what's the word? They are not moving independently. Okay? So maybe the true degree of freedom is much less than 8. Okay? Now think of 2 variables, right? If x and y are 2 variables with correlation 1, perfect correlation, you only have 1 degree of freedom. Recall. Okay? So recall that, okay? So maybe you have actually less degree of freedom. Now, let me show you what that degree of freedom looks like. Okay, I'm just going to carry out the calculation. Okay, my matrix is equal to data. Yeah, because I don't need the name. And matrix is okay, right? Now, let's see that dimension. Right? Now, I'm going to take this matrix. I'm going to take transpose. Okay? I'll show you the step first, and then we'll discuss what this actually means. Okay. If I take the transpose of this matrix, okay, what's the dimension? Oops. right? Okay. So now, what is the dimension of transpose of my matrix dot my matrix? Anybody? Yes? Well, remember the matrix? Let's go to some picture here. What does my matrix look like? My matrix looks like this, right? Right? And it's very long. Okay, and I take the transpose of it. Where's my mouse? Well, you get the picture. I don't know what happened to my mouse. Okay, there it is. If I take the transpose of it, okay, and this is 8, and this is 4,500. It's gonna be an 8 by 8 matrix, right? 8 by 4,500 times 4,500 by 8, it's gonna end up being 8 by 8. So you're gonna have 8 by 8. Okay. And that's exactly what this is. Okay. Now, okay, I'm gonna call this thing my X transpose X. Okay. I'm gonna call it my X transpose X. Okay. And let's see what it looks like in matrix form. Okay, it's just some number. It's just some number. It's just some number. Okay, a bunch of number. Now you notice something that it is what? How many columns and how many rows? What else can you notice? It is a square matrix. What else can you notice? It is symmetric. Okay, symmetric. This one is equal to that one. This one is equal to that one. This one is equal to that one. This one's equal to that one. Right? It's symmetric. Okay. So X transpose X is symmetric. Now, the property of this matrix, okay, it kind of like XTX, kind of summarize movements of all A variable. Yeah. Okay. So I'm gonna erase the word together. I'm gonna add the word co-movement over here. Okay, co-movement. So this is sort of like how they move together. How they move together. Okay. Now, you recall eigensystem. What's an eigensystem? Okay. Eigensystem is you have okay, I better use plain text. Matrix A, okay, given matrix A, eigensystem, okay, means that you find eigen vector V such that AV is equal to LV. Find an eigenvector V and eigenvalue L. Okay, such that. You guys remember that? Do you remember that or not? Okay. So what it means is that if V is, so let's say in our case, V is some eight-dimensional object. There. Okay? A, V is such that the result is stretching or shrinking. V without reorientating. Remember that? This is the video that I asked you to watch. I don't know how many lectures ago, but many lectures ago. YouTube 3 blue 1 brown eigen system. There. Okay, remember this? Right? Remember this? Right? So a vector gets moved, gets stretched, gets shrink, but in certain direction, it doesn't reorientate. So it's sort of like in the direction that it's already moving a lot. Okay, you can't move it much further. It is just, the direction is like this. You can only multiply. So that's like a sweet direction. Well, if you use this, let's go back to our thingy. Oops. Okay. If I'm going to do this, okay, I can value. Okay, let's go to this. Eigen system. Yeah, and notice it's a built-in function f1. Eigensystem of something is going to give you an eigenvalue and vector. Okay. So I'm going to call my eigenvalue and my eigenvector is equal to eigensystem of this guy. Remember, this guy summarized how the 5 yield values move together. Okay, this is how so that it captures the movement, the essence of all this movement together, right? When you study investment, like a portfolio investment, you hear words like variance, covariance, matrix, or that sort of thing. It comes in under similar kind of thinking. Okay, let's do this. Okay. Now, remember this thing is this thing, which comes from taking the data from doing this. Okay, remember this from doing this. So it summarizes all the movement. I'm gonna do this. Okay. Ta-da! Oh, looks like a big mess. What is this? Well, have no idea what it is. But I know that the first element is my eigenvector. My eigenvalue. Second element is my eigenvector. I'm gonna take this. Okay, watch this. I'm gonna take the first eigenvalue. My first eigenvalue is equal to my eigenvalue. Okay. Likewise, my first eigenvector is going to be equal to my, and I might as well go for the second. You know, I'll use it later. Okay. Oops. Okay. And might as well take my third. Okay. Now this thing is already arranged in a nice way. Oops, sorry. Okay, you see that? So right now my eigen, well, let's look at my eigenvector. My eigen. Yeah. Oops. It has 8 values. I'm just taking the first one. So that's this one. This guy is 300,767.7. And my second eigen value is 3,900. My third is 250. Notice right away that the size of numbers goes down from the first to the last. Okay, see that? The first one is 300,000. Second one is 4,000. The third one is 100. Second one 45. Third one, so it gets smaller and smaller. So notice that. Okay. Now I'm going to make this assignment and see if this is true. Okay. X transpose X dot my first eigenvector. Is it true? That's equal to my first eigenvalue dot. But it's not a dot, right? It's just a simple multiplication because it's just a number. My first. True. Right? So what this function does, what this function does, where's this function? This function, oh, I just erased it. Hold on. Okay, let me show you. Let me just get rid of some of the nonsense. Okay, this is my data. Okay, my matrix. Okay, I don't need this. I think I keep erasing too much. Okay, so my matrix, and I don't need this dimension. Okay, so my matrix is this. Okay, so you can have this and you can copy this for your project. So my matrix is that data set, my X event, and then I have this this thing that my eigenvector, value, eigenvector is equal to system of X transpose X. Okay, so I did it. And and I make this because it's quite useful. I'm going to use this a lot. So this is true, right? Same if I go to second. Okay. Oops. Why is it false? Let me show you what it looks like. Sorry, something weird. I don't know. Maybe it's something numerical because it looks the same. So let's take, I take a maximum. It's something numerical. Okay. So let's take the difference and take the absolute and then take the maximum. Yeah. So it's not exactly equal. It's just different by numerical. Okay. So this is basically practically the same. Okay. So what happened is, okay, and this is the magic. This is magic. Okay, watch this. If I'm going to look at how this thing moves, okay, remember how this thing moves, right? How this thing moves. If I take this thing and look at standard deviation, okay, of this thing, my matrix, okay. Now, what this does is simply calculate standard deviation of every column because I take the transpose, okay? So this is my standard deviation of the short-term interest rate. This is my standard deviation of the 6 month, 1 year, 2, 4, 5, 7, and 10. Notice that it has similar degree of variability, right? But I promise you that all this variability doesn't really have that many degree of freedom because they kind of move together. I'm gonna do the same thing. I'm gonna do the same thing to, well, something else. Okay, so keep this in mind. Keep this in mind. Keep this in mind, right? Now, watch. If I take the first eigenvector, okay, take the first eigenvector, right? The first eigenvector, and I multiply, okay, my first eigenvector dot, okay, dot this, and I apply it to the transpose matrix. No, to the matrix. Yeah, I'm going to get some number, a series of number. So right now I have this number. I have this number. Okay, it's like a table, right? Okay. Now, what's my first eigenvector? My first eigenvector, right? This is my first. Okay, now look, okay? Now, watch the screen carefully. This is my data, right? Goes all the way down to 4,500 rows, right? I take transpose of this, multiplied by this thing to summarize all the whole movement. Then I send it to a magic function called eigensystem. And that eigensystem breaks this down into 8 eigenvector. I'm going to take the first eigenvector, which now I will call principal component. So my first eigenvector is now my first principal component. It's just some 8 number. It's just some 8 number, right? But this 8 number sort of like tells me how the 1, 2, 3, 4, 5, 6, 7, 8 things ties together. So if I take this, okay, which is 8 number, and I take the dot product with this 1, 2, 3, 4, 5, 6, 7, 8, and I do it for every single day. Okay, if I do it for every single day, okay, so I take my first eigenvector, which I call my first principal component. Okay, I'm just going to name it. And I take this principal component. This is the way my variables are tied together. So I take this times this plus this times this plus this times, in other words, I take the dot product. I take this dot product throughout 4,500 times. This is what I get. So my first principal component time series is equal to this. Okay? You haven't seen it. I'll show you what it looks like. But I'm going to do something else. While I'm here, I'm going to take my second. Okay? And I'm going to take my third. Okay? Now I'm going to do my list plot of all these things. My first, my second, my third. Okay. Now I'm going to compare this to the original time series, basically. Okay. Anybody notice something? Okay. I haven't given you the label, but it goes blue, yellow, and green. So this is my first component, my second, and my third. Okay. Now it has the same movement through time. Okay. If I put them side by side, can you notice anything? Well, actually, let me do this. Just put the minus sign in front of it. Now, forget what I did, the minus sign. It just happened to be some technicality. Okay, now, are you seeing anything? So this is all A interest rate movement together. I make the summary into a principal component and look at the first component. The first component captures most of the movement, right? In fact, you remember this? Remember what I did? I checked the standard deviation. Standard deviation. Okay. Right? Right. Right? Now, if I do the same thing, but I take the standard deviation not of the original data, but I take standard deviation of this guy. Okay? Look what happened. This is the variability in the 3-month interest rate. This is the variability in 3 months interest rate, variability in 6 months, 1 year, 2 year, 4, 5, 7, and 10. By putting them together, right, in that co-movement thing, okay, in that co-movement XPX, and I take the first principal component, the first principal component moves a hell of a lot more. Second moves a hell of a lot less. Okay. In fact, if I were to do this, let's say to here, I'm going to do it for all of them, right? So my first eigenvector. So instead of taking just this, I'm going to take all, right? So if I take my 4th, my 5th, my 6th, 7th, 8th, 9th, 10th, it's going to get much less. What I have done is from the 8 original variable that moves in time. I created another 8 random variable that also moves in time, such that I concentrate all the movement in the first guy. Whatever the first guy doesn't capture, the second guy does. Whatever the second guy and the first guy doesn't capture, the third guy does. If I do this, the fourth component, fifth component, it's going to get so tiny, it's going to be barely perceptible. Right? Now, let's look at what these components are. We haven't seen them. Okay. Oops. Okay. Well, this is a little bit like what? Look at all the number. It's almost very close to just taking a straight average, right? Because this is about 0.3, 0.3, 0.3, 0.3, 0.3, 0.4. It doesn't differ that much. Basically, it's taking some kind of average of everyone. If I'm going to take the second, it has a different shape. It's sort of like looking at subtraction of the beginning and addition of the, right? So let's do this. Let's list plot them together. List plot my first, my second, my third. Okay, just ignore the minus sign. I can tell you later why. Oops. Some reason. Okay, let me just make correction. Watch this. The first eigenvector is like taking the first interest rate, second interest rate, third, fourth, fifth, sixth, seventh, eighth interest rate, and just sort of like add them together. Okay, this seems to be like representing how they go together. Okay, how they go together. Look at the second component. The second component is like a slope, right? It's like a slope. It's like how the short end and the opposite end goes the opposite way. Okay. And the third component looks like a curve that looks like this. In financial literature, okay, first eigenvector is called or first principle represent level shift. In other words, this is sort of like saying, I'm going to tie all the interest rate together. And if you go up, the short end goes up, the long end goes up. The short end goes down, the long end goes down. It's saying that here, on average, if you go up, everybody goes up. If you go down, everybody goes down. Up, down, up, down, up, down. Now, obviously, this is not all there is, right? So this is the representation of the movement, this movement here. up, down, up, down, up, down, 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 down. So this is what all the interest rate do together, right? It's doing it together. So all of them go up, all of them go down, all of them go up, all of them go down. So that's the movement of this line, this component. Okay, it goes up and down, ups and down. On the other hand, the second component is like how the short end and the long end have a slope, have some kind of intrinsic slope. The short end is slower than the long end. The long end is taller than short end. Okay, watch this. So that's like a difference between these. And this also moves. Sometimes it gets steeper, sometimes it gets flatter. Okay, so I kind of take the minus sign to it. So if it's positive, that means it's flattened. Okay. Okay. So now it's flattened. You know, it's the curve is doing this. So in financial literature, third, second, is represent steepening or flattening. Okay, steepening mean the interest rate at the short end is shorter than the long end. Okay, flattening is like this: steepening, flattening, steepening, flattening, steepening, flattening. Okay. The third, okay, you don't have to pay attention to this, is represent curvature or convexity. Okay. Now, here's the point. Here's the point. In life, okay. So let me put it here. Okay. By replacing 8 original time series with product with with 8 principal component, you concentrate the variability or movement in the first principal component. Whatever is left is concentrated in the second principal component, and then whatever left can concentrate in the third principal. Okay, so the first principal component will extract the direction of biggest change. Okay, in finance, first, second, and third principal component of yield curve. Level, slope, slope. Okay. Now, this happens to be almost universal in every financial market. Now, in life, let me put that here. In life, if you have, say, K time series, okay, you may need many principal components. But in finance, usually you don't even need the third. Okay, so by the time you get the first movement, so this is it. You concentrate the movement like this. So you see this this concentration here, right? So if I want to represent 8 things moving together, how would I represent it? I would represent it as everything moving together in this general shape. And this representing how it curves, steepen up, flatten, right? Okay, so this thing going down is like this line flattening, okay, and then steepening and so forth, and then flatten again, okay, and then steepen here, see, steepen, 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 and then here represents the tiny movement that has to do with the curve in the middle, how it's not a straight line, it kind of bulging, okay? So these are the 3 most principal movement in the bond market. Now in life, it's not going to be like this, right? You have a different data. So if you have, let's say I had a cancer data, it's going to have different kind of a different kind of interpretation. But it just so happens that in finance, just about, oops, in finance, okay, you only need 3. Okay, you only need 3. Sometimes most of the time you get the first one right, prediction right, and you're done. The second one is a bonus. The third one, fourth one, nobody even cares. So now we talk about 8 down to 1 or 2 to 3. Now, even if I have interest rate that goes up to 20 years, maybe I have 20 interest rate here. In finance, chances are the first one will have all the movement. Second one will have a little bit less. Okay, so this is going to be universal for finance, right? The universal is it's going to go down. The variability is go down from the first, the second, and the third. But in finance, this is dramatic. And that dramatic movement, that dramatic reduction is represented by the eigenvalue. So you can see why eigenvalue, it goes down quite a bit. Huh? Goes down quite a bit. Now it's not proportional to this, but it goes down. Okay. So this is going to be wherever you go, but in finance, this thing dominates so much. By the time you get to the set 2 component, you don't care about anything else. Okay, because the market kind of moves together, the amount for interest rate. Now let me make it more concrete by showing another example. Now this is not from finance, this is just created, it's just made up, right? In my unsupervised learning okay. No, am I not getting anything? Oops. What happened to my unsupervised learning? Becomes empty file out of sudden. Hold on. Let me go to my laptop. It's weird. Yeah. Okay, let's go to Prince. Now, this one, I'm making some data up, okay? I'm just making some data up. Now, is this obvious to you guys? Where is the big direction of movement? This is a big direction of movement, right? It's move. This is 2, 3, 1, 2, 3. This is 1. So x1 is moving a lot more than x2. Okay. Now I shift it. I make it rotate, right? And anyway, so I'm just gonna create some kind of data. Now, this is my data. It has 2 degrees of freedom. 1, 2. Remember the original the U curve has 8, right? I'm just gonna talk about 2 now. I have 2 direction, 2 degrees of freedom. So this could be time series, like moving up and down, or could just be some value. Basically, I have 2 random variables. One is x1, one is x2. But if you notice, I'm not exploring all the movement. It seems like x1 and x2 are highly correlated. So if you think about it, the principal component of movement is along this line. So just like I have 8 U curve and I shrink it down to maybe 1 or 2 principal component, in this case, let's say I'm just going to shrink to 1, okay? From 8 to 3, right? We had 8 interest rate. I shrink it down to 3 principal component and I look at those. Now I have 2 random variable and I'm just going to look at 1 principal component, okay? 2 down to 1. Where do you think that principal component would align? Obviously, the reason I make this 2 dimensions is because you can visualize. Obviously, this is the direction of movement. This is the first direction of movement. This is the principal component. This is the second, but the most important is the first. So I want to find this line. So that's what this thing does. Principal component. Okay. So let's make okay. There. You can play with this, but this is exactly it. By generating this line, okay, sorry, not this line, this data set, it has 2 dimensions. But it's not moving independently, like x1 and x2. It's not moving independently. They're tied together. So if you think about it, I want to capture the most variation in this data set. What would I do? I would take this data set. I would take this data set. Where's that data set? Where's that data set? I would take this data set there, data 2D. I take the transpose, multiply it, and I call it my covariance matrix. That's my XTX. Okay, but now I call it covariance matrix proper because I actually generated it with normal distribution, but never mind. And I do the same thing. Eigensystem, eigenvalue, eigenvector of this guy. Then I look at how they multiply. So this is actually the, let me make it as big as possible. Right. This is my first principal component. By the way, because this data set only has 2 dimensions, I only have 2 principal components, first and second. But notice the second is much shorter than the bigger one. So this is the principal component is huge. Now, that dot product is to say for every point here, if I multiply it, take the dot product to this eigenvector, I'm going to get this point. If I take a second point, I take dot product with the eigenvector, I'm going to get this point. Basically, it's the projection. So this thing that we did before, bits and pieces, this thing is my projection. Okay, so I could call it my projection onto first principle. Okay. So basically, if I take the projection along this line, it's going to have the greatest standard deviation, as you notice. If I take the projection along the second principal component, I'm going to have smaller standard deviation. Okay. Now this one I can only go to 2 because the original data is 2. Okay. So in the example, in the 07 supervised and learning B, we start with 2D ellipsoid data, and then find first and second, and that's it. So data vary the most along the first principle. Clearly. Okay, clearly. So this is the picture I want you to talk about. Okay. Okay, so we have this is a trivial example that I made, but this thing here using 10 view. So this is what's the name of the data set? There. Okay. S1. Okay. And then case. Huh? So I have 2 cases. Okay, so that's it. That's principal component. Okay. Let's stop video here and go back and restart the video.